Hello and welcome to this second video on complex number theory. In this theory, we will get involved with the vector algebra of complex numbers. So the first thing which we are going to study is addition of two complex numbers. So we have seen that if z1 is equal to x1 plus iy1 and z2 is x2 plus iy2, then the sum of these two is equal to x1 plus x2 plus iy1 plus y2. Now we are going to study the same formula and see how it works in case of a Cartesian plane. So here we have P1 is equal to x1 plus iy1, that is this guy, and we have P2 is equal to x2 plus y2, that is this guy. Now, since it's a vector plane, what we can do is we can take OP2 and move it here. That is, this coordinate will shift to this, and this coordinate will shift to this. So now we denote this particular point as P is equal to x plus iy. Now if you draw this line, then you will find that this is equal to x1 plus x2 plus iy1 plus y2, and I'll show you how. So once we have moved this here, if you drop a perpendicular here, and if you drop a perpendicular here, and perpendiculars over here, then OL will be equal to MN, will be equal to P1K. And this will be equal to, which is y1, that is P1M will be equal to Km. And Kp will be equal to P2L. So if all these values can stand, then you will see that OP, that is this coordinate, is equal to this, which is our y1. And this is, this is y2. That is Pk is equal to P2L is equal to y2, and Kn is equal to P1 M, which is equal to y1. So Pn is our y1 plus y2. Now OM is our x1, and OL is equal to Mn, which is our x2. Now this is equal to P1K, so this is equal to x2. So ON will become x1 plus x2. And that's how you sum two complex numbers and vector plane. Now the same thing is repeated here in theory. Now we are going to subtract two complex numbers. So we have P1, which is x1 comma y1. We have P2, which is x2 comma y2. So what we can do is we can take a negation of P2, that is minus x2 minus y2. Once we have taken negation of this, we can do the same as addition with P1 and P2. So what we do here is we take this and we bring it here, or rather it is incorrect to say we take this. We take rather OP2 and we bring it here. That is P1P is same as OP2 prime. So once we have that, following like previous diagram, we can say that this particular coordinate will be x1 minus x2 and y1 minus y2. So the only thing which we have done is we have taken a negation of P2 and used that instead of P2, and rest of it is just the summation. So the final value of subtraction will be x1 minus x2, and y coordinate will become y1 minus y2. The same thing we have talked about, the same thing in theory here. You can read this. Now we will talk about multiplication. So for multiplication, it is very convenient to use Euler's formula. So suppose Z1 is equal to R1 EI theta 1 and Z2 is equal to R2 e to the power I theta 2, where R1 and R2 are the modulus and theta 1 and theta 2 are the arguments. Then suppose we have P1. Now this length is R1, and the angle which it makes with x-axis, which is given in green, is theta 1. We have P2, which is R2 into e to the power I theta 2. So the argument is theta 2 given in blue, and the length is R2. And if you multiply these two, the argument will be R1 R2, and the angle given in red will be theta 1 plus theta 2. That's how we multiply two complex numbers. Now division is similar. So the resulting modulus will be R1 by R2 and angle will be theta 1 minus theta 2. So it's the same, just that modulus is R1 by R2, similar like multiplication, and argument will be I theta 1 minus theta 2 because when you divide, powers will get subtracted here. So in this case, since theta 2 is larger, it has become negative, that is come below the x-axis in the fourth quadrant. So that's how we do the division of complex numbers. Now I will go through three important geometric results of complex numbers. So suppose we have a complex number Z1, we have a complex number Z2. Let's say that P represents Z1 and Q represents Z2. Then Z1 minus Z2 is equal to OP minus OQ. That is OP minus OQ, which is equal to QP. So once we have QP, the modulus is given by the length of QP. An argument of Z1 minus Z2 is the angle made by QP with x-axis, which is theta. Now we consider another diagram. We have P1 here, which is Z1. We have Q here, which is Z2, and we have R here, which is Z3. Now, if you want to find out theta here, then theta is alpha minus beta. That's very simple to examine by looking at the diagram. Now, alpha is nothing but argument of Z3 minus Z1, and beta is argument of Z2 minus Z1. So we can say that theta is equal to argument of Z3 minus Z1 by Z2 minus Z1. So similarly, if these three complex numbers are vertices of a triangle, then those vertices you can compute, right? Now, for concyclic quadrilaterals, there will be 4 points, Z1, Z2, Z3, and Z4. Similarly, you can examine and verify that argument of Z1 minus Z2 by Z1 minus Z4 into Z1 minus Z3 by Z2 minus Z4 has to be 0 for the quadrilateral to be concyclic. So this again has been left for you as an exercise. Now we are going to study the root of imaginary numbers. Now suppose there is an imaginary number IY such that it is not equal to 0. This is an extra is equal to. Such that it is not equal to 0, then we take the nth root of IY and we say that it is A. So IY will be a to the power n. Now if A is real, then a to the power n will be real. But a to the power n cannot be real because left hand side is imaginary. That means a to the power n is imaginary, and that's why a will be also imaginary. Now we are going to compute square root of a complex number. So suppose the complex number is z is equal to x plus iy, then we assume that square root of x plus iy is equal to another complex number a plus ib. So take square of both sides and we get x plus iy is equal to a square minus b square plus 2abi. Now we compare the real and imaginary parts and we can write that x is equal to a square minus b square and y is equal to 2ab. Once we have this, we can write a square plus b square is equal to square root of a square minus b square whole square plus 4a square b square. Now we have these two equations, and from these equations we can say that a is equal to plus minus square root of x square plus y square plus x divided by 2, and b is equal to plus minus square root of x square plus y square minus x by 2. That's how you find the square root of a complex number. Now we are going to consider another very important concept, which is cube root of unity. It is very simple actually. Suppose x is cube root of 1, then x cube will be 1, that is x cube minus 1 will be 0. So we will have this as the product of x minus 1 into x square plus 1, x square plus x plus 1 is equal to 0. Now if x minus 1 is equal to 0, then x will be minus 1. And if x square plus x plus 1 is equal to 0, then it will have two roots, minus 1 plus minus square root of minus 3 by 2. Don't worry if you don't understand where this comes from, because once we have studied quadratic equations, it will be quite clear how to compute this root. For now, you just take it on face value, or you can try to substitute this in this equation, and then you'll find that it is actually true. So now, if this is minus 1 plus minus square root of 3i by 2. Now if you take omega as minus 1 plus square root of 3i by 2, then you will find that if you square this, it gives the other root. So the three roots are 1, omega and omega square. Now if you substitute omega over here, it becomes 1 plus omega square, so it is equal to 0. Now also if you substitute here, x is equal to omega, then omega cube is equal to 1, which is the other property of cube root of unity. If you actually sum these, you will find that it is equal to 0. And if you actually multiply this, then product will be 1. So with this, we come to the end of this part of complex numbers. And next part, we will deal with more geometrical figures and more concepts involved with something like parallelogram or rhombus or interpretation of equations given in complex number. So if you found this video useful, please subscribe to the channel and like the video so that it reaches more people and more people get benefit from it, because that's the sole purpose of making this video. So I'll say goodbye here. See you in the next video, and if you got something to say, you have a question, you can ask me in the comments. Thanks a lot for watching. Enjoy.